started. So we're gonna talk about binary values and also the number systems. The binary number is used in nowadays today the computing system. So firstly, what do you think a computer system? I will give you 3 minutes to answer the question. What does a computing system include? They say computing systems are dynamic and it consists of hardware and software. So what's the difference between hardware and software? And the hardware represents the physical elements of a computing system, like the printer, the circuit board, the wires, cables, the CPU, the memory, anything. A lot of you has also mentioned in your answers. While software represents the programs that provide the instructions for the computer to execute. Okay, so today in this chapter 2, we are going to refer to this information layer to get to know about the data, how we represent data in the computer. So in this chapter, we have a goal that firstly, we need to distinguish among the categories of the number. And I think this can be, most of you has already accomplished this part. You learned this from your high school or senior school. And then you need to know how to describe the positional notation. What does the positional notation represent? And you need to know how to convert any numbers in any other bases to base 10. Base 10 here represents the decimal number system we use in our daily life. And also in the contrary, you need to know how to convert any number in the base 10 to the numbers in other bases, like base 2, base 8, base 16, right? Which means represents the binary, the decimal, the binary, the octal or octal, and the hexadecimal. So then you need to know how to describe the relationship between the bases 2, 8, and 6. Okay, they have some relationships. In fact, it is also related to the next one that is explain the importance of computing bases that are powers of 2. So 2, 8, 6 are all the powers of 2. Okay, so why it is important for the computing based on these kinds of bases, the power of 2. So let's bring these chapter goals to start today's chapter 2's contents. So firstly, we say the category of numbers. I think all of you have already learned this in your maybe primary school or in your high school anyway. All of you has already learned that any number can be divided into natural numbers or negative numbers or integers or rational numbers. Okay, so for what is a natural number? It includes 0 and also any number obtained by repeatedly adding 1 to it. Okay, that is natural numbers. For example, all these 3 numbers are natural numbers. Of course, 0 is natural number, and then plus 1, anything can be calculated by this approaches can obtained by these approaches is a natural number. So of course, all these 4 numbers are natural numbers. And then the second category is negative numbers. That means a value which is less than 0 with this minus sign. Okay, for example, it's minus 24, minus 1, some number like this. They're all less than 0, so we call them negative numbers. And then the integer is a natural number plus a negative number plus 0. Okay. In fact, 0 is also included in this natural number. So in fact, it is a natural number plus a negative number. Okay, so it could be positive, it could be negative, but it is all related to this number 1. And the last category we call them is rational number. It represents an integer or the quotient of 2 integers. The quotient of 2 integers. Okay, so it can be represented like this. So it includes the integer and also the quotients of 2 integers. So get to know the categories of the number is quite important because we represent different number in these different categories. use different methods to represent them in the computing system. So firstly, let's know what is the natural number and how we understand the number in the decimal number system. So we can understand what does it mean if a number is in a binary number system or in other number system. What exactly does this number represent? What does it mean about this number system? So if we consider, firstly, we consider the decimal, which means base 10, what we use in our daily life. We consider how many ones are there in this 642. If it's in decimal, we call it 642, right? So I listed 3 here. Obviously, it represents the first one, right? Because I call it 600, means 600, then 40 and 2, right? So it can be written in this way. So we can say in this number, in fact, we have digits, right? We have 3 digits, 2, 4, 6. And these digits are organized in some specific positions or in some specific sequence. So the position represents a lot of things. The positions represents, for example, the position here, in fact, no matter the digits is, it represents how many hundreds, right? So here represents the how many tens. Here means how many ones. Okay, how many ones, how many tens, and how many hundreds. Okay, so in each word we have, firstly we have digit, secondly we have position, and each position represents different meaning, and this meaning is closely related to the number system, right? Because the number system is 10, so here it is 110, 100. If the number system is 8 or 13 or other, it would be totally different. Okay. So we can see in decimal 642 is 640 and 2 in base 10. So the base of a number determines, firstly, it determines the number of digits. That means, for example, if in base 10, then the digits are from 0 to 9. The digits smaller than 10, okay, because 10 is 2 digits. So we have 0 to 9, 10 different digits in this base 10. So the number of digits is determined by the base. If the base is 8, then we only have 8 digits from 0 to 7. If the base is 2, we have only 2 digits from 0 to 1. Okay, so the base determines the number of digits. So in base 10, we have 10 digits from 0 to 9. And secondly, it determines the value of digit positions. Okay, because I said it represents the 1, 10, 11, 100 because the base is 10. Okay, so it determines the value of digit positions. Okay, so 642 in base 10 positional notation, we can write them like this. We can write it 6 times 10 with the power 2 plus 4 times 10 with the power 1 plus 2 times 10 with the power 0. So here we have a base. Base is 10, so we write the number in base 10. Base is here, and it has a power. The power indicates the position of the number from the right to the left, and from 0 to increase it. So 0, 1, 2. So the power would be 0, 1, 2 from right to left. We always from the right to left. Okay. So if we construct it in the abstraction expression, we can write an expression like this positional notation and this formula. Here represents the digit, and here represents the position or the number of digits in the number. Okay, the n here is the positions from 1, 2, 3 until n. Okay, it represents the position. So D is a digit. R represents the base. For example, base 10, then here 10. And the power here represents the position 2, but it is from 0 to 1, 2, 3, 4, 5 until n minus 1. Okay? So when we have this abstraction position notation, we can represent any number in any other digits, not only base 10. For example, still this number, 642. If the base is 13, what does this number represents or how many ones in this number. So it becomes 6 times 13 with the power 2 plus 4 times 13 with the power 1 plus 2 with the times 13 with the power 0. And we do the calculation, do the addition of all these numbers, and finally we can got 1068. So that means 642 in base of 10, in base of 13 is equivalent to 1068 in base 10. Okay. Okay, so do you know how to do this calculation? Use this positional notation. Okay, so you can say in decimal it is base 10 and we have 10 digits from 0 to 9. So in binary it is base 2. So we have 2 digits, 0 and 1. So we can conclude for a number to exist in a given base, it can only contain the digits in that base, which range from 0 up to, but not including the base. Okay, smaller but not including the base. So any base is represented as 10 in any base. The base number, for example, 10 in decimal is 10. 2 in binary is 10. Okay, so any base in that base representation, it is 10. Then, let's see here, base higher than 10. We use what kind of digits? We use A, B, C, D, E, F. So this is hexadecimal. We call it, we have a base 16. It's a hexadecimal. So here A represents 10, okay? Okay, so next, we are going to know how to convert octal to decimal. For example, we have a number 6, 4, 2, and we say it is octal number. So that means we have a base 8. How could we invert it to the decimal number? We use a positional notation, right? We use 6 times 8 with the power 2 plus 4 times 8 with the power 1 plus 2 times 8 with power 0, and it equals 418 in base 10. So how we convert hexadecimal to decimal is in a similar way, right? For example, if we have a number DEF, what do we do? The D represents 13, right? So it is 13 times base 16 with the power 2 plus E represents 14. So it is 14 times 16 with the power 1. And also plus F represents 15. So 15 times 16 with the power 0, it's 1. So we do the calculation, it's supposed to be 3,568. Okay, so remember the digits in the base 16 are from 0 to 9 and A to F to represent from 10 to 15. Remember this and do the practice how to convert different number systems number to decimal. Okay. So the last one would be convert binary to decimal. Okay. So we have binary number 1101110. How we convert it to decimal, it's similar, and we, in fact, we are always through right to left and right from here, from the right, because we do not know the notation of the positional notation of this position. So we always count from the right to the left. So it would be 0 times 2 with the power 0, and 1 times 2 with the power 1, and also 1 times 2 with the power 2, and also 1 times 2 with power 3, and 0 here, and 1 here, 2 with power 5, and also 1 here is 2 with power 6. And we do the calculation and we obtain the results. It would be 110. Okay, so this is how we convert octal, hexadecimal, and binary numbers into the decimal number. We use the positional notation. Okay, so that's almost all for today's class. And for the next class, we are talking about arithmetic in the binary, how to do the addition, how to do the subtraction, and how to do the converting directly from the binary to octal and decimal, or decimal and octal to binary, without transfer them or transform them to the decimal. Okay. So how we convert between these number digits, number systems from the base of power of 2.